we're happy to have Cara Giovanetti from Berkeley to tell us about primordial deuterium.
Thank you. Thanks for the invitation. I'm really glad I was able to make it out here this semester. I'm going to be talking about some new work I've been doing with Tim Wanders, who is a graduate student at BU, and his advisor, Han Liu. Now, I heard that someone in the audience had their laptop stolen at BU, and so I hope no one's got any lingering ill will towards the institution here. I hope this is going to be some exciting work I can update you guys on. Before I jump in and talk about deuterium, whenever I talk about BBM, the first question I always get asked is, well, what about lithium? And so I will spend one slide trying to convince you that there is no longer a problem in primordial deuterium, or in primordial lithium, excuse me. So if you are not familiar with the lithium problem, the way it goes is that you can predict the abundance of primordial lithium as a function of the baryon density, that's this purple curve here. You can measure primordial lithium, that's the height of this small yellow rectangle down here, and you can look at all of the values of your predicted lithium abundance that are consistent with your measurement, and that gives you an inference for the baryon density. But the CMB also tells you what the baryon density is, that's this green rectangle here, and you can also use that to infer what your primordial lithium abundance should be, so it's all the way up here. You see it's quite discrepant with what's going on over in measurement. So this is a long-standing problem in early universe cosmology. It's known as the lithium problem, but there have been some recent measurements that have cast doubt on the existence of this problem. The way people would do this is they would look at stars, and they'd say, okay, there's lithium-6 in this star. Lithium-6 is really fragile, and so if you have any lithium-6 at all, you can assume your lithium-7 is not being depleted. So they were doing these measurements, they found lithium-6, they're like, great, we can infer lithium-7. In 2021, some folks went back to check these stars out, and they found no evidence for lithium-6 in these stars. And so that suggests that the value of primordial lithium-7 that they were measuring was being depleted from its primordial value, which would be consistent with what's going on over here. If you're really up on the literature, you may also be aware that there have been some new measurements using the interstellar medium rather than just stars to measure primordial lithium. This is probably the way to go. The problems with it so far, though, are that it agrees with the measurement from stars. And now we know that the measurement from stars has a systematic, and so that makes me a little bit skeptical of this new measurement. There are a lot of systematics that are hard to control when you do the ISM measurement. And so last February, a bunch of folks in the BBN community got together for an online workshop, and we reviewed all of this evidence, and the consensus that we came to is that we are probably not measuring primordial lithium-7. And so this is sort of the status of the lithium problem. This is why I'm not going to be talking about it for the rest of the talk. It's because, in my opinion, there really isn't any problem there at all. We can't yet measure primordial lithium-7. Okay. One other quick bookkeeping item before I can get into the meat of the talk is notation. Yeah, please.
That's the question about this, since you're mentioning it. I don't know very much about this at all, but and so this, the question of whether the metallicity of stars, this has been a long-standing issue. I remember way back, even when I was a kid. But there's not. Does theory have anything to say about this? I mean, like star formation theory, or is this just one of those questions that's so incredibly detailed that the models can't even come close to getting it? Where is that?
There are a lot of open questions as to how you would go about modeling this in the star. The other reason people really thought that they were measuring primordial lithium-7 was this speed plateau, right? Where like you look back far enough and the metallicity, the lithium-7 as a function of metallicity starts to plateau, right? People are like, okay, cool, that means when we measure these stars, that lithium abundance should be roughly primordial. People have now made even lower metallicity measurements of these stars, and they found that the plateau goes away. And so no one really knows what the right stellar evolution model is that we would need to try to predict what the primordial lithium-7 abundance is.
Okay.
Yeah, it's a complicated problem.
Okay, thanks.
Thanks for asking. Okay, so one other thing I need to get out of the way real quick is notation. I'm going to be talking a lot about nuclear reaction rates in this talk. You're probably a little bit more familiar with the notation here on the right. This is what we use in chemistry. You have your initial state over here, your final state over here. There's an arrow in between. In nuclear physics, people like to use this notation here on the left instead. It means the exact same thing, except instead of an arrow, we put a comma. these parentheses mean a little bit more in the context of like nuclear physics experiment. We will not be using that extra information, so you should just think when I see notation like this, here's my initial state to the left of the comma, here's my final state to the right of the comma. It's completely one-to-one with the chemistry notation you're a little more familiar with. I will try to use the notation on the right when I can, but sometimes this crops up because it's more compact, so just don't freak out when you see that. Okay, so now I can finally start my talk. I'm going to start with an overview of BBN, just to wake everybody up. It's a Monday, but also to focus in on some aspects of BBN that maybe you aren't so used to thinking about. I'm going to be talking about the current status of determinations of the primordial deuterium abundance. I'll compare different things that two groups have been doing to try to figure out what is the standard model prediction for primordial deuterium. And then in the third section of the talk, this is going to be the longest section, I'll talk about this new method we've been developing to get this prediction right. If there's time at the end, I have just 2 slides about what all of this means for new physics. So we'll see if there's time for that. I don't see a clock anywhere, so someone should yell at me when I have 5 minutes left. Okay, so let me start with this BBN overview. So BBN is Big Bang Nucleosynthesis. It's the period between 2 and 20 minutes after the Big Bang, where protons and neutrons are fusing to form the first light element nuclei. It is an epoch characterized by high temperatures. We're looking at roughly MeV to keV scale temperatures. We're starting to approach the kinds of energies you might start to see in particle physics experiment. But the densities are astronomical. The energy density in radiation, for example, is enhanced by a factor of 10 to the 40. And then finally, the timescales are really long. We have 20 minutes where these protons and neutrons are all interacting, and so you're able to probe things like weak interactions, which you can't always probe in things like particle physics experiment. And so studying BBN is highly complementary to a lot of other efforts in particle physics. People know this, and so they frequently use BBN to try to constrain all kinds of new physics models. So this, I just Googled really quick, like BBN new physics, and just picked a couple of different examples, but the archive is full of papers like this, where you use the precision and sensitivity of BBN to understand lambda CDM or place constraints on all different kinds of models of new physics. And the reason you're able to do this is because BBN is characterized by very precise predictions and very precise measurements. So over here, I'm showing an example of how we predict these kinds of light element abundances. These are the abundances of different light element nuclei as a function of time or temperature during BBN. I'm not showing error bars on this plot, we usually don't do that as a function of time, but the uncertainty on the final predicted abundances of deuterium and helium-4 are roughly percent level. Meanwhile, over here on the right, I'm showing an example of how we measure these kinds of light element abundances. This in particular is for deuterium. This is the absorption spectrum from a pristine metal-poor gas cloud passing between us and some bright background quasar. The quasar is very bright, we know its emission spectrum, and so we can study these absorption features to figure out the relative abundances of different elements in the cloud. So in particular, these little wings over here on the left are telling us about the abundance of primordial deuterium. The Gruber Prize in Cosmology last year was awarded to the authors of this paper for their determination of the primordial deuterium abundance to 1%. Just this morning on the archive, there was a paper that determined the primordial helium-4 abundance to 0.5%. And so we're very good at measuring these kinds of light element abundances. And so we're able to test our predictions for new physics in this very precise lab, I would say, for cosmology. Please.
Well, just out of curiosity, like how many of these clouds are there roughly, like in these determinations, how many it involves, how many of these clouds do you have?
I believe there are 8. It is statistics limited. And so I will talk about this at the very end of the talk. And how we can get even more precise determinations of the primordial deuterium abundance by finding more of these systems. There are folks who have a plan to do so, and so I'm excited by that.
Why is it more reliable than lithium?
You are not modeling this inside stars or anything like that, so you just have a very low metallicity gas cloud.
But I thought they tried it, lithium with gas clouds, and it agreed with the stars.
Interstellar
wrong.
Yeah, so it's a different environment. So here you are looking at a cloud that's backlit. And the cloud is quite far away from you. You're able to measure the metallicity in the cloud. With lithium-7, they were looking at like emission in the interstellar medium, so it's a very different setup. With deuterium, you get very lucky in clouds like this that the deuterium lines are just slightly shifted from the helium lines because it's almost the same nucleus. And so you can only use this method when it comes to deuterium. You can't use it for helium-4 or lithium-7. Please.
Maybe this is probably a stupid question.
No.
Is there any fundamental connection between roughly 10 to the 2 seconds and roughly a tenth of an MeV? They sort of line up.
Fundamentally, no. I mean, if you have a new physics scenario, like you may also change your clock. Like if I inject a bunch of entropy into photons at some point early on, this will shift around, but this is just sort of how it lines up in like the CDM. Great. So I'm not in the business of doing measurements. I am in the business of doing predictions. And so you may ask, how do I get predictions like this? The answer is usually code. This is a code block diagram for a VBN code I wrote called links, but really they're all kind of the same under the hood. They factor the calculation into two primary components. You have one piece that's responsible for your background. This is doing your thermodynamics. It's computing Hubble, it's computing the photon and neutrino temperatures, it's computing the scale factor and your time. Once you have that background cosmology for the scenario you're interested in, you can pass it to your abundances module. The abundances module is the giant coupled set of Boltzmann equations that you use to track all of your light element abundances. In order to construct this coupled set of Boltzmann equations, you need some input from nuclear physics. You need to build a reaction network. Once you have done so, you have the relevant coefficients for your Boltzmann equations, and then you can finally predict your primordial element abundances. What I mean by reaction network can be depicted graphically like this, where I have a node in my network for each nucleus whose abundance I'm trying to predict. And then I have lines that take me between each of these nodes. These are different rates. And so this is telling me, for example, I have two rates that take me from deuterium to helium-3. I have one rate that takes me from deuterium to tritium, and so on up the chain. The reaction network answers questions like, how efficiently do my reactions proceed? Are they exothermic or endothermic? How much energy is involved? And how do these rates change with temperature? Once I have the answers to all of these questions, I can put them into my VBN code, and then I can get my predictions for my primordial element abundances. Questions so far? Mostly good on this? You look like you have a question. Yeah.
How do people actually compare and keep track of this type of calculation with a lot of steps, a lot of details? And like if we want to say something about BBN, what is required to convince the community that you are not doing wrong thing?
Like, is your question like, how do you know you're not making a mistake somewhere along the way?
Like if I claim I have a documented model, I want to say BBN haven't read out yet. Do I have to run a whole calculation, or I just worry like no one has done it yet, so it's not real yet?
That's a good question. So usually you would have to take a BBN code and you would have to hack it to put in your model of dark matter, and then you'd have to run it over a bunch of different combinations of parameters. And you would find the regions where BBN allowed or even preferred your model, and you would find the regions where it's ruled out.
And if you don't want to do that for your project yet,
then you're out of luck. There are certain estimates you can do. So like if you estimate the neutron fraction, for example, then you can figure out whether or not you mess up helium-4 pretty easily. And that's something you can just kind of do by hand. But if you really want to do like precision cosmology and understand whether your model is allowed, typically it requires hacking some code.
That's a good opportunity to make friends.
That's true. Yeah.
Really, seriously, right?
Yeah. Is there a question in the back?
Yeah, so just wanted to follow up a little bit on that. So for example, can you go to the previous slide? The one before where you showed the spectra?
Yeah.
Yeah, can you say a little bit about, so for example, on the spectra you measured the line strength, I believe.
Yeah.
So how do you actually like connect those measurements to, what do you say about the primordial?
So it's incredible. For deuterium, that's just it. So they find these low metallicity gas clouds. They understand that the metallicity is a little bit higher than it was early in the universe, but since the systematic error, since the statistical error is so large compared to that systematic, they don't even bother to extrapolate it back. That's just it. For helium-4, there's some extrapolation involved, though there was this new paper this morning, and I'm not actually sure if they still have to do that extrapolation. But yeah, for deuterium, that's the whole story.
Okay.
Thanks.
So just to make sure I understand the basic
Yeah.
physics here. So these are atomic spectra, but you're seeing the nuclear masses because there's some recoil, right?
Right.
That the kinematics is shifting
Yeah.
these peaks
This
just
is,
a little bit.
This is a tiny, tiny shift
Yeah.
here. It's incredible that they can
Right.
like get these well-separated peaks. You look in like old textbooks, like Donaldson's textbook has like one of these spectra, and the helium or the hydrogen line just like completely consumes the deuterium line, and it's just like this little dip. So this group got incredibly lucky, found these amazing systems, and measured them with these very precise telescopes to get these spectra.
Okay, thanks.
Anything else? This is great.
Sorry, what are the units on the x-axis?
Yeah, I was going to.
It's velocity relative to their absolute redshift in kilometers per second. So it's you should see this as you should compare it to speed of light.
Okay.
Yeah. Okay.
So that's in units where the speed of light is what? Not 1, but not 3, but anyway, there's something weird about that. I'm sure those units it's a very small change in the velocity, right, on the horizontal axis, but it says 50 and it says relative to 3, so that's a little confusing.
So there's a cloud with some extent, right? And so they say the center of the cloud is at a redshift of 3. And then they're
Right.
measuring
But what does 50
deviations.
mean? Like that first tick says, what is 50? What does the 50 mean?
You can understand that as like part of the cloud is receding from you at a velocity of 50 kilometers per second.
It's in kilometers per second,
Right.
whereas whereas the going rate is some reasonable fraction of the speed of light.
Exactly.
Right? Yeah.
Yeah. So
It's
it's
a very,
amazing.
very small shift.
Okay. I'm going to move on because I'm worried you guys are going to start asking me questions about measurement that I can't
Yeah.
answer. So I'm going to keep going. Great. So we have this reaction network, right? And this is what we need in order to create connections for our primordial abundances of light elements. I am going to be focusing in on these particular reaction rates. And so just to give a little context, I want to just give a little bit of background for how people measure some of these different reaction rates. This is not going to be comprehensive, but just to give kind of a flavor of what people are doing. Most common thing, as far as I can tell, for these BBN reactions is to use a windowless gas target. So the idea is, let's say you want to measure deuterium. Deuterium goes to proton and tritium. So you'll have a gas target that's all deuterium. You'll have a beam of deuterium. You will fire your beam into your gas target, and in here there is some array of detectors that will detect your reaction products and the angle at which they were emitted. Back in the day, people just used to have like these big open windows into their gas targets, and then they realized that introduces a lot of systematics. So now they have these really complicated systems of vacuum pumps that basically seal off their target chambers to the world, except for the beam that's allowed to penetrate. And so this is more or less the industry standard. There are some sources of uncertainty in systematics that you have to watch out for. The gas density is non-uniform, so you have to correct for that. The gas target can heat up the longer you run the experiment, and so you have to be aware of that as well. And so while they're able to beat down their error to maybe a couple of %, there are some of these normalization errors that stick around. So you also have to be aware of these systematics. You may ask, okay, well, if I have this uncertainty from non-uniformity of my target, can't I just use a solid target? And that would be a great question. People are doing this as well. This doesn't completely solve your problem because the target can chip or deplete as your experiment runs, and so you still end up with some of these systematics as your experiment runs. And then the last setup I want to touch on is not exclusive of either of these. It's something you can do in addition to some of these setups, and it's this Trojan horse setup. So remember, the process we want to measure is deuterium. Deuterium goes to proton and tritium. The problem is at very low energies, there's a large systematic from electron screening. My target is neutral atoms, and so at low energies, my beam can polarize my target and artificially reduce the Coulomb barrier. That's not very good if I want to measure just the bare cross-section. And so what the Trojan horse protocol is instead of firing a deuterium beam at my target, I'm going to fire a helium-3 beam at my target, and then once inside the electron screening potential, that helium-3 converts to a deuterium nucleus and a spectator proton. And so this gives me access to the vertex I'm interested in, but I don't have to worry about electron screening. This is kind of cool. It works as far as avoiding the systematic, but it is impossible to know the overall normalization of the signal when you do things this way. And so you have to normalize to other experiments. And so each of these setups will introduce some normalization error, and this is going to be relevant when we try to fit a line to the data that are coming from nuclear physics experiment. But fine, once you have all of your data, you can go ahead.
Sorry.
Please, yeah.
Maybe totally ancillary, but how do you make a helium-3 beam?
Oh, I don't know. Yeah, I understand it's not that hard.
Okay. Very
There
cool.
are a lot of
order
facilities
one on
that can do
Amazon?
it. Yeah, maybe. Buy one secondhand. Yeah. Thanks. No, I don't know the answer to that
Okay.
question. That's great.
We should just build a collider, clearly.
Yeah,
Really?
obviously.
Cool particles.
Yeah. Okay, so once we have our helium-3 beam and we have our data, you can fit a line to it. You can either fit a polynomial to it. There is also a theory prediction for what these rates should be as a function of energy, and so you can also choose to use that information if you so choose. We'll talk a little bit more about that in a couple of slides, but either way, you fit a line to this data, and this is the line that goes into your BBN code when you're constructing your reaction network. Any other questions so far? Okay, so if you're very astute, you'll notice that on the y-axis here, I have put S. I was not too lazy to put sigma for cross-section. This is not the cross-section on the y-axis here. This is the astrophysical S factor. And the reason for that is that cross-sections are kind of tricky. They have a strong energy dependence. They're usually non-monotonic as a function of energy. This y-axis can span many orders of magnitude, and it's kind of a pain to fit a line to this kind of shape. Especially if I only have data in the tails, the curve I fit to this data will be very sensitive to things like investigator choice. So to avoid this, the thing we all do is we do an energy-dependent transformation of the cross-section. We define this astrophysical S factor precisely to get rid of this bump coming from the Coulomb barrier, and so when I do this transformation, I get this nice, smooth, monotonic function that looks like this. And so this is way easier to fit a line to, and so when the experimentalists give me their data, they give it to me in terms of the S factor. I have to convert that back to get a cross-section, and then finally the cross-section is not what goes in the code. What goes in the code is a rate. So the last step is to integrate the cross-section against a Maxwell-Boltzmann distribution to get a thermal average cross-section and finally a rate for each of these reactions. So I have to do this for every single reaction in my network. We're good on that. Okay. So that's everything I wanted to say in terms of background for BBN. I want to now move on and talk about some of the specific techniques people have been using to determine the primordial deuterium abundance. There are two teams in particular whose efforts I really want to focus on. The first is the group that wrote the BBN code Parthenope. Parthenope is a Fortran code. It was written in 2008. It got a major facelift in 2018, and so it's state-of-the-art. It's actually what the Plump team uses when they want to do their BBN-informed fits with the CMB. And the Parthenope team says the deuterium abundance is 2.51 plus minus 0.04. For reference, the measured deuterium abundance is 2.53 plus minus 0.03, and so this is in great agreement. But on the other hand, we have the determination from the Primot team. Primot is another BBN code. It's written in Mathematica. It's a lot newer. It was released the first time in 2018. They did a ton of work to improve their helium-4 predictions. So they reworked their calculation of proton-neutron interconversion. As a fun aside, they also have a huge reaction network. So they can predict primordial abundances up to oxygen 20. And so if you have an idea to measure primordial nitrogen, these guys can get you a prediction for what that should be in standard cosmology. But in any event, all of these details notwithstanding, the Primot team says that the primordial deuterium abundance is 2.44 plus minus 0.04. This is just about 2 sigma lower than the measured abundance. Now you may ask, okay, well, why are they different? Is it because this code has these better helium predictions or has this larger reaction network? Is it because one of the codes has a mistake? And the answer to those questions is all no. In fact, it just boils down to the choice of rates used in the reaction network. So again, these reaction networks are where all of this experimental input is coming in. If you open up these reaction networks, they usually look something like this, where for every reaction in your network, you have as a function of temperature, a rate, and then an uncertainty on that rate. And if you look very closely at the rates that the Primot and Parthenope teams are using for these two reactions that are so critical in determining the deuterium abundance, you find that they're a little bit different. And so this is really what the difference boils down to, is that they've chosen different values for the rates for these two abundances. And in fact, if you run Primot but use Parthenope's choices for these reaction rates, you get the same number as the Parthenope team did. And so we can just show that this is really the primary difference between the codes. Question?
So naively, I should just conclude that they probably both underestimated their errors.
No, you should not, because one of them probably didn't, right?
Well, no, but I mean, that part of
The numbers
error
they're
should
putting
be-
in are
the
totally
there should be
unreliable.
propagating the uncertainties of the measurements, including how you parameterize them or whatever, or which measurement should, I mean, what, so I don't understand.
You
Please explain.
You don't know a priori if one of them is just way off and one of them is spot on, or if both of them are a little bit wrong. And so I'm very allergic to the suggestion that you should just blow up the error bars because there are two ways of doing it.
No, but okay, well, maybe you'll just tell me the rest of the story. I'm just saying that somewhere along the line, the choices that were made in using these different reaction rates, I would guess that they would both have said that they are within the errors that they finally quote.
Oh, right, sure.
In that sense.
So I hope to convince you by the end of this talk that there is a right way and a wrong way to do these fits. And then that is not the approach we should have taken even before we do this, because there was a chance that there was a right way and a wrong way to do this.
Okay.
Are you saying that it's based on the same data and just different fits to data?
There are slight disagreements about the right data to choose, but the bigger difference, as I will talk about on the next slide, is just how you choose to fit a line to this data.
Like some of these points, the error bars look like they're 10 to the 8.
All the errors are identical. In that case.
These are, the units on this guy is a little bit funny. This is actually the log uncertainty. But were you seeing 10 to the 8?
Well, the measurement is 10 to the minus 8 and the uncertainty is 1.
Oh, sure, at these super low rates. But you should consider this as an additive factor on the log rate, not a multiplicative factor on the base rate. Okay.
Why don't we call
It's pretty
it?
I'm
remarkable that it's the same for every part of the
No,
energy
it's
range.
not. I won't get into that, but I'm happy to chat about that offline. Okay, so what is the difference? As I mentioned earlier, they do make some different choices about data sets to include, and I'll talk about them in a little bit. But really the key difference is that they're making different choices about how to fit a line to this data. So the Parthenope team is using phenomenological fits. They are fitting a polynomial to this data. And this is the team, remember, that says the standard model prediction for deuterium agrees with measurement. Meanwhile, the Primot team is using information from that theory curve. Remember, there's a theory prediction for what these rates ought to be, and so the Primot team is using some of that information to do their fits. And this is the group that says there's a deuterium tension in lambda CDM. So the first thing that these groups have to do is data set selection. So this is a slide I stole from Elaine Koch. He's on the Primot team. And so here he was describing why the Primot team made the choices it did when it was time to do data set selection. And you see that they don't really choose a lot of data sets. They're very selective, but you may worry, do they even have enough data? Are they influenced too much by one data set or another when they don't use as many data sets as they can? This column over here, this Passanti plus column, is the Parthenope team, and they are a lot less selective. They use a lot more data, and so you may ask, are they using contaminated data? Are they using data that doesn't pass a certain quality cut? And so both of these teams are making some different choices. For the most part, as I'll talk about at the end of the talk, this doesn't matter as much, but it will become kind of an important detail. Once they have made their choices about what data to include, the next question they have to answer is how are they going to fit a line to that data. So the Parthenope philosophy is to follow the data. I'm just going to take all these different data sets and I'm going to fit a low degree polynomial to them. I'm going to do standard chi-square goodness of fit fitting. I'm going to find the polynomial or the right parameters for my polynomial curve, and I'm going to call it a day. There is a little bit of a caveat. If you remember earlier, I was really harping on the fact that a lot of these nuclear physics data sets have these large normalization uncertainties, these large systematics. So the way that the Parthenope team will incorporate these systematics is to add an extra parameter for each data set in their analysis. So this parameter controls the overall normalization of each of these different data sets. So they're independent, but basically the data sets are just allowed to float up and down in the plane, slightly penalized by the magnitude of the systematic uncertainty to provide a better fit to the data. So the number of degrees of freedom, or the number of parameters in this model, is the degree of the polynomial plus the number of data sets. It's a relatively flexible fit compared to what I'll describe on the next slide. What the Primot team does, by contrast, is to use what you know. So they're going to use the fact that there is a theory prediction for what the astrophysical S factor should be as a function of energy for some of these rates. Now, this isn't a slam dunk for them because the uncertainties on this theory prediction are really hard to track down. And this curve is only known up to about 0.6 MeV. So even though we have data for some of these rates up to 3 MeV, they can't use it because they don't want some extrapolation of the theory curve biasing their fit. But okay, once all of these caveats are taken into account, the procedure is more or less the same. They add one additional parameter for every data set to account for the fact that there are these systematic uncertainties. And then to account for the fact that it's a little bit hard to know the nuclear theory uncertainties, they're also going to allow this theory curve to float up and down in the plane as well. So this has fewer parameters.
Can you just kind of get an idea, this 0.6 MeV, how big of a deal is that? I mean, is that within the dominant range where you're actually using those cross-sections in primordial BBN?
What a great question. I will talk about that at length towards the middle of the talk.
Okay.
When they did this fit, it was not clear. The kind of common wisdom was that roughly about 2 MeV was the cutoff. So what they were doing is they would do their fits and then they would extrapolate the theory curve up to about 2 MeV. Good question. Good. But this is a less flexible fit than what was going on with the polynomial, right? I only have one overall parameter controlling the shape of my curve, and it's just the overall normalization, rather than some degree of a polynomial I get to play with. Okay. But this is about it. I have polynomial fitting versus effectively template fitting, and that's the major difference between these two analyses. So that's everything I wanted to say about this previous work, and I'll comment a little bit more on it a little bit later. I want to talk about now a new method, but I see there's a question in the back. Go ahead.
Yeah. So I'm slightly surprised that Primot team, they use like less number of data sets compared to the Parthenope team, given that they have this one floating parameter for theory because they're going to be like degenerate.
So it's not completely degenerate. Each parameter for your data sets has some penalty because you know the systematic uncertainty. And so if the systematic uncertainty is 1% and I'm changing my normalization by 10% to get a good fit, then I'm going to get a harsh penalty for doing something like that. And so that does break these degeneracies, even though the motion is the same. Anything else? Great. Okay, so I'm in the business of using BBN to put constraints on new physics. I wanted to know what the right value of primordial deuterium to use was, and so we got together and we decided we were just going to fit our own line to this data. And so to do so, we are going to do something very flexible. We're going to use Gaussian process regression. If you're not familiar with the Gaussian process, it's basically a fancy interpolator. You assume that your data are drawn from some highly multivariate Gaussian. When you do that, you get a closed form expression for what intermediate values of your data should be, and you also, as a great bonus, get a closed form expression for what the uncertainties on those draws should be. So what we're doing here is we're not making any assumptions about what the underlying functional form should be. I'm not saying it's parameterized by some low degree polynomial or by a curve of this shape. I am interpolating. And when I get my result from my Gaussian process, I will have a distribution of functions that are a good fit to my data. I don't want to give the impression that it's completely model independent. There are kernel parameters that you have to optimize to indicate your correlations. You have to make a choice about how wiggly these functions can be or how much variance you can tolerate. But there are established methods to optimize these kernel hyperparameters. And so it's not as if you're kind of just making choices about this willy-nilly. There's kind of an established procedure to get these. So let me just show you how this works. Let's say I have a data set that looks like this. So I have 6 or 7 data points. I'm asked to fit a line to this data. I get a little nervous if you ask me to do that because I wouldn't be sure if I should use some odd degree polynomial, or maybe I should include include a sinusoid or something like that, my result is going to be very dependent on investigator choice. So I'm not going to do that. I will not assume any kind of functional form. I will use the Gaussian process that's effectively going to give me this interpolation. So it's not perfect interpolation. You see, this point is very uncertain, and so my Gaussian process mean is only going to kind of kiss the bottom of it. It's not going to go right through the center of the point, and that's considered a feature. Meanwhile, this point is not very uncertain, and so the Gaussian process mean goes right through the center of that point, as it should. But since I assumed that my data are drawn from this multivariate Gaussian, I also get this nice closed form expression for what the uncertainty on my fit is. And so now I have a distribution of functions that are a good fit to this data. I can draw functions out of that distribution, and each of those draws looks something like this. So each of these kind of squiggly curves provides a good fit to my data. And so with this, I can sample this space of functions. I can account for the fact that my data and my fit are a little bit uncertain. And so I can effectively run samples like this through a BBN code to get my deuterium abundance. Go ahead.
Yeah, maybe I just feel like I'd like to understand this just a little bit better. So you have this very large space of functions, and then can you just say a little bit more, like, what is the Gaussian thing? I mean, what are you doing with this giant space of functions? You're certainly not finding trying to find the best thing in that huge set.
Good, yeah.
So you're somehow taking a sample, but could you just say a little bit more about
let me think
what is
there.
it you're optimizing, for example? Like, what is being optimized by this?
Let me say it another way. So rather than thinking about this as a space of functions, all I'm trying to say with the Gaussian process is that there are correlations between my data points. If I know my function at x of 10, and I know my function at x of 22, I'm saying I have some information about x of 15. That's really what's going on fundamentally. The fact that it gives you this distribution over functions is just a way to interpret the result of doing that.
So somehow the space of functions is somehow capturing these correlations.
I guess I'd go the other way around. But yeah, it's because I'm assuming that there are these correlations that I'm allowed to get functions with arbitrary
I'm saying
properties.
if you use very, very wiggly
Very
functions
good.
here,
Yeah.
then you would not get any information, right? Because the information would be washed out.
Good.
The fact that you're using functions with a certain smoothness is somehow your model for how the correlations are working somehow.
Let me put a pin in that you're on the right track. There's a
Okay.
question over
Anyway.
here.
Well, it's related. I just was trying to understand my own way that
Yeah.
you're not trying to find a fundamental, simple sine wave or
No.
polynomial. You just want a really well motivated spline or interpolation method
Exactly.
for predicting other
Yeah.
x values.
That's exactly right.
Y values or
Yeah,
x values.
I want to be able, when I run my BBN code, I want to incorporate the fact that the data that come from nuclear physics are uncertain. So I want to know what's a good fit to those data, and then what's the uncertainty on my fit. And this is a great way to do that in a purely data-driven way. Okay, so ordinarily when I get to this point in the talk, I give folks the option. Go ahead.
Sorry, can I also just ask, so what is the red curve in the center, what is that optimizing?
What do you mean by optimizing?
Well, if
There's
you
one
have a
curve.
fit, that's optimizing something, right?
Minimizing or maximizing.
Yeah.
No, there is no optimization involved.
Well, how do you
finding the Gaussian
choose that
process
curve?
mean.
How do you choose that curve?
Okay, so ordinarily in this part of the talk, I would give folks the option, and I'd ask if this is a sufficient level of detail, or you guys want me to talk about math. But this crowd very clearly wants me to talk about math, so I'm going to talk about math. So this is how the Gaussian process works. You asked for it. Yeah. Here's how it works. Everything on this slide that does not have a star is my real data. So I measure my data at some abscissa x. I get values of my function that are y, and then my data are uncertain, characterized by some static uncertainty or matrix sigma. I want to know the value of my function y star at new x values x star. This is interpolation, right? There's a gap in my data, so I need to know what's the value of my function between those gaps. We say in a Gaussian process that my data can be characterized by a multivariate Gaussian. So I have some mean and some covariance describing that highly multivariate Gaussian. Now, because this is a Gaussian, I can just solve, I can do some exponential matrix math, and I can get a closed form expression for what my y star should be in terms of the new means mu star. So remember, this is the mean of my multivariate Gaussian describing my interpolated points. I do a little bit of more exponential matrix math, and I get a closed form expression for what those means should be. Now, the means are a function of my kernel. I'll touch on that in a second. They're a function of the uncertainties on my data points, and they're a function of the actual data values y. The kernel is encoding information about the correlations that I am assuming my data should have. The kernel says, if I know f at x1, what information do I have at f of x2? So this is where there's a little bit of hyperparameter optimization involved. But I am not optimizing anything to write this down. There is no optimization step happening here. Everything is closed form. It is determined the moment I decide to do a Gaussian process. The only thing left is for me to pick the right kernel. So let me show you what a kernel sometimes looks like. So this is the kernel that most people tend to use. This is the squared exponential kernel. You can use a lot of different kinds of kernels if you so choose, but this is kind of the textbook option. You have two hyperparameters characterizing your kernel. There is a kernel amplitude. The amplitude is telling you how much variance can I tolerate in these functions that I'm trying to have to be a good fit to my data.
So I think I'm not understanding something very basic. I mean, when you had your curve, you have a y-axis and you have an x-axis,
I do.
right? And so this is, the kernel is just a function of the x
Right.
values.
Yep.
And is the idea that it is a Gaussian in this function k? In other words, you say it's a Gaussian, so
Yes.
but it's a Gaussian in these k's, and these k's are functions themselves that you are choosing, or that you're inputting.
Very good. So I am saying that my data, my y values, are characterized by a multivariate Gaussian. I am saying that the covariance matrix of that multivariate Gaussian involves these kernels. And so the kernel is just telling me how correlated are different points. I don't need to know the y values to say x1 is really correlated with x2, or x1 is not correlated at all with x2. And so that's the information that's contained here. I don't care about the actual values, it's just saying these 2 points are close together, and therefore they should vary with each other.
Maybe I can ask you like this, because I mean, I find this very interesting. It seems sort of different from the way we think about in high energy particle physics. You know, we think about statistics, we think about either frequentist or Bayesian statistics.
Good.
And the way you sort of understand what those things are is you have this picture, like the frequentist picture is you do the experiment over and over again, and how often do you get this versus that.
Very good.
Okay, let's just stick with that, because I don't really get Bayesian. But
Yeah.
anyway, is there something like this here? Like this
Yeah.
is the answer to some precise thought experiment, which then you can argue about whether it really describes what you're really doing.
Good.
But that's how I think of, statistics, is that it's a
Good.
very mathematically well-defined
Yes.
sort of toy problem that you can see how it has something to do with what you're actually doing, right?
Yes, very good. So
is there,
if your data are truly drawn from a multivariate Gaussian, then the uncertainty that you get on your data can be interpreted as a Bayesian, like, confidence interval or whatever the
maybe you
credible
can say,
interval.
what does exactly it mean drawn from, the data is drawn from a multivariate Gaussian?
So I believe there is some distribution underlying my data. Maybe it's a polynomial, maybe it's a straight line, right? And then maybe it has some uncertainty, so that when I do my measurements, I am somehow probing the parameters of that distribution.
Yeah.
In the Gaussian process, I am saying that distribution is a highly multivariate Gaussian.
I guess okay, maybe you should go on, but I'm not sure what that last phrase means. But okay, just
It
go
takes
on.
a little
I
bit
think
of
I have the
chewing, yeah.
idea, the general idea enough to go on. I don't
So
want to
why?
stop you.
Because we only see one variable on the x-axis. So where are these other dimensions? Or that's what I'm having trouble with. So
I know, this is not-
multivariate means multidimensional Gaussian.
Yeah. So I have
So there are
however
other.
many data points I have and however many data points I want to interpolate at, that defines the dimensionality of the Gaussian. Question in the back.
But isn't the uncertainty, isn't that actually on y? and not an X, but you somehow use that sigma for
What-
the
what do you-
density in the kernel.
Good. So very good. When I am putting together my covariance matrix for my Gaussian process, I need to somehow encode the fact that my data are correlated with one another. And so here I am saying X is very correlated with itself, except it is not. It is not very correlated with itself because there is some uncertainty on my measurement. Does that kind of make sense?
Right, but okay, yeah.
It takes a little bit of chewing, yeah. Anything else? How am I doing on time, by the way?
Probably you should, well, I think you're, I mean, if nominally you have like 15 minutes.
Okay.
But I mean, I think
This is great.
we're
yeah.
stopping you. I mean, I
No.
think, at least for me, it's interesting.
Yeah.
That's why I'm asking, because
I'm-
this is
I'm-
not the way you're used to thinking about data or fitting or whatever. So anyway, but maybe you can try to make sure you get through the rest of your story.
Sure.
Right? I think we want to hear the end of it.
until 3.
Yeah, we have the room until 3, but maybe we'll, stop and clap, and people who need to leave can leave, and the rest of us can stay. But yeah, please maybe try to get, through your
Okay,
story so
I'll
we can
push
hear.
forward a little bit.
Yeah, we can hear the, the
Okay.
whole thing.
So just to give a little bit more intuition for what this kernel is doing. This kernel is saying, if I know f at x1, what do I know about f at x2? And so I can pick a form for this kernel. It's got 2 hyperparameters. The first is the kernel amplitude, and it tells me how much variance can I tolerate. Do I have a lot of information about f at x2 or very little information about f at x2? It's going to determine the size of my error bars, basically, on my fit. The other hyperparameter is this correlation length tau. So there's this exponential term in the kernel. It's saying if x star is very far from x, then my overall kernel amplitude is going to be very small. But what I mean by very far is calibrated by the size of this correlation length. So let me show you what this looks like. If I just plot the values of my kernel for 2 input vectors, 1 and 2, and I fix my hyperparameters to have an amplitude of 1 and a correlation length of 1, this is telling me that x star of 6 knows very little about what's going on at x of 1. For example, my correlation length is itty-bitty, and so 6 and 1 are really far away from each other when I choose these values for my kernel hyperparameters. I can make different choices. I can say what happens if I set my correlation length to 10, and so now I get a very different picture, and it says, okay, well now actually 1 and 6 are very close to each other, and so I know things about what's going on at x equals 6 if I have information at x equals 1. And then finally, you may also ask, what's this kernel amplitude doing? If I set my correlation length back to 1, but jack up my kernel amplitude, it looks a lot like this first picture, but note that the scale on my color bar has changed. And so what this is going to translate to is a lot more variance in my fit. So let me just show you what happens when I try to fit some data using this kernel and these parameters. These are the same data as before, but you can see this is not such a good fit to the data. I have this huge variance because my kernel amplitude is enormous. And I don't really have like smooth interpolation here because I've said my correlation length is only 1. So I have x at 10, I have x at 22. I know nothing about x at 17 because 17 is really far from both 10 and 22 when my correlation length is only 1. I can make different choices about my kernel hyperparameters. Now I've set my kernel amplitude down and increased my correlation length, and so now I get something a lot smoother. My correlation length is 10, and so if I know x at 10 and 22, I know x at 17 pretty well. And so when we actually go and do a Gaussian process, we don't just kind of look by eye and see which ones provide a good fit to the data. This is where the optimization step comes in. The way we do this is called a leave one out cross-validation. Basically, we want to ensure that our Gaussian process generalizes well to new data. So what you could do here, for example, is run your Gaussian process, but take one data point out. Then you put that data point back in, and then you compute some likelihood estimator to see if your Gaussian process was a good fit to that data point that you left out. You can do that for every data point in your data set, and that lets you know that you're not overfitting, and you're providing a good fit to your data, and you're really learning the underlying properties of that distribution. Okay, so this is what we did. Really, I should say the first thing we did is data set selection. So we picked these 5 data sets here, and we fit a Gaussian process to 3 3 key deuterium rates. So there are 3 rates that are really critical in determining the deuterium abundance. They are the 2 that the Premont and Parthenope teams disagreed about, and then there's this 3rd one that was measured recently. I fit a Gaussian process to it, so I get a mean, that's this black curve, and some uncertainty on the distribution of functions that are a good fit to my data, which is the gray shaded region here. Once I have performed this fit, I can sample this posterior in order to sample the uncertainties on my measured data. So the squiggly lines here, I know they're a little bit hard to see. These are all good fits to my data. And so by doing this 10,000 times, I can capture the uncertainty from my nuclear physics data, and I can get an inference of the deuterium abundance that has a very principled error bar on it. So this is what we...
Why is it able to extrapolate with such small error bars?
Good! This is a great question. Let me put a pin in that.
Okay.
Yeah, good. Okay, so we did this, and by we I should say Tim. Tim did this, and this is the result that he got. So the gray shaded region is the measured deuterium abundance. Your prediction for primordial deuterium depends on the baryon density. And so the 3 different histograms here are the result you get assuming the ACT, Planck, or SPT results for the baryon density. Fiducially, we choose Planck because it's the one in the middle. And so when you say, okay, you use Planck omega b, you use the Gaussian process to fit these 3 rates. The determination of the primordial deuterium abundance is 2.45 plus minus 0.04, which again is more or less 2 sigma lower than measurement. We can compare this to the existing results in the literature, and we can see exactly why we agree with the Premont result, but disagree with the Parthenope result. This is just one of the rates. I am showing here the actual rate that goes into the code, so not the S factor, but the rate itself. I've normalized everything to our mean rate. So the Gaussian process mean is at 1. The gray shaded error bar is the uncertainty on our rate. The pink error bar is the mean and uncertainty on the Premont rate. That's the one that had the deuterium tension. And the blue shaded error bar is the mean and uncertainty of the Parthenope rate. And remember, Parthenope is the one that says there's no deuterium tension. But you can see we pretty much exactly recover what the Premont team is saying this rate should be. We disagree very strongly with what the Parthenope team says this rate should be, and so it's no surprise that our value for primordial deuterium agrees better with the Premont result. And just so this is easier on the intuition, a low rate means high deuterium because it means this forward reaction is slow. Yeah?
Remind us why we care much more about 10 to the 9 versus 10 to the 8 temperature. Like at the lower...
Let me come to that.
Okay.
Yeah. Good, we haven't gotten there yet. Okay, so I was shocked when I saw that. I thought Tim made a mistake. I'm like, there's no way that the super flexible Gaussian process agrees better with the template fitting from Premont than it does with the polynomial fitting that the Parthenope team was doing. And so we combed through this result really carefully to try to figure out exactly why we were disagreeing with the polynomial fit. And we've identified, I think, 3 reasons why it's very challenging to fit a polynomial to these data. So the first is a little bit more to do with dataset selection. There are systematics at high energy that were previously undiscovered. But because the Parthenope team chose to include some of this high energy data, they end up introducing a bias because of these systematics and having an inflexible polynomial to fit their data with. The second reason also just really surprised me. It turns out that if you assume that the data are drawn from a distribution described by the theory curve, you cannot provide a good fit to that data with a low degree polynomial. And I'll show you what I mean by that in a couple of slides. The last reason I'm not going to get into too much today. I'm happy to chat about it offline. The Parthenope team is doing a frequentist analysis with a penalized likelihood, and we think there is some ambiguity in how they're defining their likelihood that is causing them to vastly underestimate the size of their error bars. I'm happy to chat about that offline, but I'm mostly going to focus on these first 2 items. So, what is this data? SE, the astrophysical S factor, is not a rate. It is not the thing that goes into the code. The thing that goes into the code is this guy. It is a thermal average of the cross-section, which is the transformed S factor. Now on paper, this thermal average extends all the way up to infinite energy. That's a problem because I don't measure my cross-section all the way up to infinite energy. But fortunately, there's this Maxwell-Boltzmann guy who's really suppressing everything above some certain energy threshold. And so we did an experiment, much like the questions y'all have been asking, about what really does this upper bound need to be in order to get a good fit to the data. And so all we did was we started by cutting off at 3 MeV, where the highest energy data were, and then we just sequentially lowered this upper bound bit by bit. And what we found is that our prediction for the deuterium abundance is not sensitive to whether you cut that integral off at 3 MeV or whether you cut it off at half an MeV. So this means you don't actually need any data above half an MeV, because you can just set your cross-section to 0 at half an MeV and it has no influence on your predicted deuterium abundance. And in fact, there is danger in including this high energy data if you don't necessarily need it. So again, these are screen grabs from Elaine Coast's slides. He was talking about their rationale for excluding this particular data set that the Parthenope team does include. There is also a theory prediction for what the ratio of these two rates should be. All of these measurements are measuring both of these rates. If you take a look at the ratio of these rates for this data set at the top, this Tubino 2014, it's these yellow triangles here. And you see that these yellow triangles lie very far off what the theory prediction for this ratio should be. It doesn't even really turn over at the right point. And so this suggests that there is some kind of untracked systematic in this data set that is potentially influencing any fit that uses this data. And in fact, we just wanted to see what's the influence of including this data when you use a low degree polynomial to fit the data, and this is what we found. So that Tubino data from the last slide are these goldenrod points here. The Parthenope team is including that data set and one additional high energy data set. But because this data set has a systematic, we're finding that it pulls the high energy part of this polynomial low. What that does is in the region of energies you actually care about for this S factor fit, you are in fact lower than all of the data. So even if they had just cut off this data set at some threshold energy, they would have gotten a better fit to the data. But because they included all of this high energy data, and because it probably had a systematic, it biases their entire rate low. There is no data set that wants an S factor this low in this region of energy space. And so I think this is one of the reasons why the Parthenope team is finding a higher value of deuterium than us or the Primot team. The other reason is because it turns out that the low degree polynomial just cannot fit data described by the theory curve. So the way we looked into this was we generated some mock data. We said, okay, the truth is going to be the theory curve, and I'm going to invent a bunch of mock data sets that are drawn from a distribution characterized by the theory curve. Now I know the underlying distribution, so I know how well my fitting is doing. And so we fit our mock data sets with a Gaussian process and with a low degree polynomial, and this is what we found. So again, I've normalized everything now to my generating function, so the generating function is the theory curve. Over here on the left, I'm showing the results from trying to fit data drawn from the theory curve by a Gaussian process. And you see, over most of this energy window, it does very well. There is a slight caveat at very high energies, because when you exclude that data set with the systematic and the other high energy data set well above the BBN relevant energies, there is no data left in this region of space. And so then you can see the Gaussian process starts not to do very well. And this is related to your question from earlier. When you have no data, it tends to vastly underestimate the size of its error bars. It doesn't just explode. So there is some residual uncertainty here, but the region that's more important for BBN starts roughly about here. And so we do a phenomenal job of fitting this data with the Gaussian process. The same is not true of the low degree polynomial. So the Parthenope team uses a degree 2 polynomial for this rate. And we find that in this region that is so critical for determining the deuterium abundance, again, they are systematically underestimating the value of this S factor. And so their rate is biased very low, and therefore their deuterium abundance is biased very high. And this is just because the theory curve has this weird little elbow in this region, and the degree 2 polynomial just can't capture that very well. It systematically will underestimate the value of that curve. So it seems like systematics from high energy data combined with an inflexible model are explaining why one group was finding one value for deuterium and why a different group found another value. Now the Gaussian process, very fortunately, is not susceptible to either of these issues. We can even include this high energy data with the systematic, but because our fit is so flexible, we can just kind of absorb that systematic, and it doesn't bias our fit down at these low energies that really matter. So all signs are pointing to this very mild tension in primordial deuterium. This was a lot of work for 2 sigma. You may very well ask whether you should care. I think that's totally a fair question. I think my genuine
We might not
feeling-
even take you to dinner, so.
Not that.
2 sigma,
2
come on.
sigma.
It's a coffee break.
Yes,
Yeah.
right. We've already bought her a tea, so we're done.
Yeah, so it's absolutely a fair question to ask. Is 2 sigma really worth all of this? My genuine feeling is it is worth keeping an ear to the ground about. It is not time to go ambulance chase and model build the 2 sigma deuterium tension. I think that is premature, but there is reason to believe that this could get worse in the relatively near-term future. The first reason for that is that this is not the LHC. We are not measuring billions of events and trying to put a significance on them. We only measure 2 abundances. We measure deuterium and helium-4. And so drawing something 2 sigma away from your prediction already is already a little bit lucky. But fine, it's still only 2 sigma, and so it should still be taken with a grain of salt. As I mentioned earlier, the deuterium measurement is statistics limited. And there are upcoming plans to use 30-meter telescopes to observe orders of magnitude more quasars, and therefore orders of magnitude more pristine systems that have deuterium you can measure. And so, again, these are these 2 guys who won this big fancy cosmology prize last year for their determination of the deuterium abundance to 1%. And so they have a plan to do it again and to potentially beat the uncertainty on the deuterium measurement down by almost another order of magnitude. And so this is something that could happen in the near-term future that would give us a lot more information about what exactly is going on with this discrepancy. On the nuclear physics experiment side, I mean, this is the dominant uncertainty on the theory prediction, so we need some new measurements of some of these deuterium rates. There was one in 2020 or 2021, and that was great. That's why I wasn't talking about this one dp gamma reaction with the Prima and Parthena B teams, because they agree on what that rate should be, because now they have super precise data, and it's kind of impossible not to fit it very well. But for these other deuterium reactions, we need to measure them again, and so I am trying to poke some folks and needle some folks about getting these measurements done. But if you know people who do these kinds of measurements, please put me in touch with them, because we would really like to get some more data to hone in on this a little bit more. Because I'm roughly out of time, I'm going to skip the new physics stuff. I'm happy to chat about this offline with anyone who's interested. The punchline is that this is a really easy tension to model build if it sticks around. It's not like the Hubble tension where you have to bend over backwards to get it to work. It really is very simple, I think, to get this guy to work. So I will just skip through this for now and just leave my conclusions up for you to take a look at and stop there. Thank you.
Questions?
Yeah, all right.
So I noticed that it keeps, like, whenever you don't have, like, a point, it just tends to, like, drop to 0, or, like, it always, like, curves downwards.
You like this guy?
Yeah, like, I would assume that since you're constraining it, that you know something about these points, why wouldn't it, like, kind of act like rubber bands where it just, like, stand in both directions? Why does it just drop to 0?
Very good. So basically what this example is saying is that I did not take data at a fine enough resolution. I really should have taken data at every 1 x value and not every 10 x values. But now, because I don't have those intermediate data points, it's not really fair to just draw a line between them when my function might really be doing something like this. You know, this is what you're saying when you pick these values of these kernel hyperparameters. The reason why it drops to 0 is just one detail on this slide that I did not mention, and that's this mean mu. This is people call it a prior. You can set really any value you'd like here. So when you have your actual data, You don't know the multivariate Gaussian that they're drawn from, and so you do have this little extra degree of freedom here that you get to play around with. And so I just fixed this to 0, and that's why this keeps dropping down to 0. Had I fixed it to 10, then it would have just gone back up to 10, if that makes sense.
I mean, I feel like it'd be more proper in terms of like your uncertainty for it to do a straight line rather than going to some fixed.
By allowing it to interpolate linearly, you're making an assumption about what the underlying functional form is. And so by choosing a correlation length that is this small, you are saying to yourself that is the wrong thing to do. And so instead, what you really want is to choose a larger correlation length, because you want to say, I do know something about the points in here. Does that kind of make sense?
Can I ask something about that? So I was trying to make a cartoon in my head about what this thing is doing. And so I have a partial guess, and you can tell me if I'm just completely wrong, but it can't be completely right either. So if I imagine that I was trying to drive through these points, okay? And so, but I have a constraint, which is that I can't, the correlation length is sort of that I can't change my direction arbitrarily fast.
Can't be too wiggly.
I can't be doing this. So I got to slowly, and I might have to turn over, and that qualitatively explains, and I think that what the rate at which I'm allowed to turn my steering wheel is essentially somehow parameterized by this correlation length.
That's a good way to think
Very
about
roughly.
it. Yeah.
But then, how should I then, if this analogy isn't totally stupid, how do I think about the amplitude? What is that?
So if I had picked a much larger kernel amplitude
Is that like
here,
the maximum direction I can turn?
it's how much variance you can tolerate. So if I were to choose a larger correlation length here, you would see the error bars between these points blow up.
Yeah, but
But
what would happen if I change sigma bar?
Yeah, good. So that's what happens. Oh, sorry, did I say correlation length? When you change the amplitude, you would see these error bars blow up. But when you went to draw functions from that distribution, you'd find that they're still very smooth. They don't do this when you draw them, even though the variance
it's the
change.
probability. So I'm actually randomly steering, kind of, and seeing how likely. Okay. It's not that I'm optimizing my steering. I'm
Very
sort of
good.
randomly steering.
Yeah.
And then seeing how often things go well.
I think
Something
you're
like
on the
that.
right track. If
Okay.
I understand your
I know, I
analogy,
mean,
I think you're going in the right direction. Yeah.
Okay.
So, how does this compare to loss fitting?
What do you like? Just defining a loss function.
LOESS.
Yeah.
LOESS.
LOESS. So I don't know what that is.
It's an acronym for locally optimized something or other.
I haven't heard of it.
Okay.
Yeah.
There's another paper to be written.
Yeah. Okay.
Yeah, redo it with LOESS.
You got it. Like what qualitatively is that? Can you give me a
It's
flavor of it?
qualitatively trying to avoid overfitting.
So I have no risk of overfitting when I do this.
But that's what it claims, that it avoids overfitting too.
Is
so
it just another interpolator?
It's some kind of interpolation.
Okay.
Yes.
I mean, anything that is deep in the interpolation regime will not overfit, so I imagine it would be just as good. Anything else? Yeah, please.
Can you do the final connect the points, no pun intended, to show that this style of interpolation fully explains the result from that other collaboration?
Like why it agrees with the Premont
Yeah.
result? So our feeling, why does it totally out? So our feeling, based on based on this result. So the fact that we can accurately fit data that are drawn from a distribution described by the theory curve, and the fact that we agree with Premont so well, says to me that the theory curve is pretty close to the truth. And so the fact that the Premont team is just using the theory curve as a template and floating it in the plane is a pretty good thing to do, just because the theory curve is very close to the actual distribution that these data are drawn from. That is my feeling. That is a really hard statement to prove rigorously, but at least we also know that the theory, the Premont procedure is not susceptible to these issues that the Parthenopy procedure was susceptible to. So I think there's a world in which you could fit this data with some polynomial-like thing, but it can't be degree 2 to 4. It has to be some very high degree polynomial to get it right. But I don't think there's anything in particular magical about the theory curve itself. It's just that they don't have to worry about systematics at high energy because the theory curve cuts off at 0.6 MeV, and so they got very lucky and they just throw out all of that data that potentially has that systematic. And I mean, it is an inflexible model, but it just happens to be very close to the distribution these data are actually drawn from.
And since, while I'm speaking,
Yeah.
how long are we going to have to wait for the much larger data samples you talked about? With the,
Maybe 5 to 10 years. Yeah.
and that will put this to rest, or
I
show
assume that
the-
will put this to rest. It would be even better if we could get the nuclear physics data too.
Well, it will put the measurement to rest. And
It would put the-
then
yeah,
there's-
very
they
good.
also want to get the theory.
Yeah,
It'll
I
put
mean,
them both to rest.
Yeah,
right?
I
Both
could
of the
always
answers.
use more precise measurements of the deuterium abundance. You could drill that down forever, and I would be happy about that. Because like it gets to the point where like, you know, we use nuclear physics to learn about BBN, but you can also use BBN to learn about nuclear physics. And so if you can drive the uncertainty on the deuterium prediction way down, you can start to use that to infer properties of the rates. And so I think there's always more to learn. Like, let's just keep doing measurements of these, you know, forever. But as far as this particular tension is concerned, it should be like 5-ish years, I think.
And how long for the deuterium collider?
So when I visited CERN last month, I was told as early as this month. Then I emailed the folks who were going to do that measurement, and they're like, we're having problems with bureaucracy in Germany, and so it might be a little bit longer. We're trying to get beam time in Michigan. They might be able to help us with a rate measurement like this, so we're really pushing on it. But it's unclear whether any of this is really going to materialize soon or not. So if you know folks who can help us out, please connect me with them.
There's a beam over there.
we prefer our beams charged. So,
Tough.
In Crocker, isn't there a deuterium beam?
good question.
Maybe you should talk to Eric. Maybe you should.
Right, we have a little historic cyclotron next
Cool.
door, and our director Eric Previs is also professor in the physics department. Is interested in exotic stuff like this, so
Okay.
maybe we should put you guys in contact.
That'd be great. Thank you. Professor in the back.
Just wanted to make sure that I understand the 2 sigma tension.
Okay.
So you showed these 2 results initially, and yeah, they are from 2 sigma. But aren't these from the same exact data sets? So shouldn't the error bars be correlated? So is it really like 2 sigma, or is it?
So I never compare the Parthenope result with the Premont result. I only compare the Parthenope result with measurement and the Premont result with measurement. And so the Premont result is 2 sigma away from measurement. And that is the uncorrelated statement I know I can make. Good catch, yeah.
Should we
Yeah.
clap and
Maybe
maybe
it's time,
continue
yeah.
discussions afterwards?